Hi, in this video, I'll be continuing the journey on series and we'll look at more tests to show when a series converges. In the previous video, I went through what is a product of series or convolution, and in this video, we'll make use of that to help us find out when series converges. So we'll start with this formula known as the summation by part. It's something like analog to your integration by part that I've done in a calculus video, so you can check that out. And for summation of parts, it's like the formula just for summations instead. And so you're given two series, and you know two sequences, and you know the series of AKs, the partial sum you label as capital AN. Then the series of the convolution of P to Q will equals to this new series plus AQBQ minus AP minus 1 BP. And really it's because AN equals to capital N minus capital A minus N minus 1. And so then you just need to multiply in and rearrange the terms to get this following series. And then you can just prove that this expression equals to over here. Because now you see here is from P to Q minus 1. So you just need to take from P to Q minus. So you just need to take out the Q term here. And add in the P term here. And then you're done. Which is how you get this following result. And so you don't really need to memorize this summation by parts formula, and really you can just derive it on the spot by just remembering the technique of treating AN as capital AN minus capital AN minus 1. And so with that, this summation by parts formula will help us in proving the Dirichlet test, and this is because the partial sums of AN, if you know the partials, and that's saying that if you know the partial sums of AN form a bounded sequence, and you know that BN is a monotonically decreasing sequence that converges to 0, then you know the convolution product converges. And this test is really useful whenever you see a series of a form that you can split into two series that fulfill these conditions. And the reason for this is because you can choose a M such that AN is bounded by it. And because you know BN converges, given an epsilon, there is an integer such as BN will be less than or equals to epsilon over 2M. And then you can put from P to Q, and using the partial summation by parts formula, you get this following results. And you know ANs are bounded by M, so you can pull out the M, and you get the following over here. And then BN minus BN plus 1 this whole thing will be just 2M times BP. And the reason for that is because you can just expand out this and you see that you can cancel out the terms, and then what you're left with is 2 times of BP. And so, because this is telescoping sum, and so because BP is less than epsilon over 2M, it will be less than epsilon. And so the convergence follows from the Cauchy criterion for convergence. And so we're done. And this proves when a convolution product can converge. And a variant of this or a corollary is that if now you know that you have a terms Cn which are all positive and strictly decreasing, and you know that one of the term is positive, the other one is negative, and so on, so it's alternating positive negative, and then you know that Cn converges to 0, then the summation, the series Cn will converge. And this is known as the Leibniz alternating series test, and really you're just applying the Dirichlet test to these two following series and you're done. So this proof you can just see it because this will imply this. And so you can see how it's used here, where we prove the convergence of the alternating harmonic series because the terms are one positive, one negative, and then the terms strictly decreases in absolute value. And so by the alternating series test, it converges. Next, we shall prove Abel's variant of Dirichlet's test, and it says that if the partial sum converge sequentially, and that Bm forms a bounded monotone sequence, so it will be convergent, but it may not converge to 0 now, then we know that the series An, the convolution product of the series, converges sequentially. And that's because if Bn approaches B, then Bn minus B approaches 0, and then we just apply the Dirichlet test with An being the partial sum of summation An and beta n being Bn minus B, and then we know that this series now will converge, and as a result you can expand out this beta to be Bn minus B, so this equals to summation of alpha of An times Bn minus summation of An B. This will converge, so you bring this over, and so this term will converge as well. And so we are done. And so you can see how most of it is just applying Dirichlet's test. And so we can see an example to see how it's applied. And so if we are given that An converges, then you want to prove that the summation of 1 plus 1 over n to the power n times An converge. So by Abel's variant of the Dirichlet test, you can see that we just need to show that 1 plus 1 over n to the power n converges. And that's easy to check that the limit is the Euler number. And so by the Abel's variant, because we know that An converges, we just need to show that this part is bounded and monotone. Or you can just show that this part converges, which is bounded and monotone in R. And so you can see how the Abel's variant of Dirichlet's test is being applied. And so that's all for this video. It is a simple video where I showcase to you when a convolution sum will converge and what test do you use, which is the Dirichlet test. And with that, you come two corollaries of the alternating series test and the Abel's variant of it. And so that's all for this video. I'll catch you in the next one. Bye!